Hello and welcome to another video. In today's video we're going to be going over topic 1.5, continuity. Alright, well, a function is continuous on a number if the limit as x approaches a of f of x is equal to f of a. Well, what does that really mean? Let's sketch a graph. Oh, geez, this is not wanting to work. Alright. There we go. There we go. Now suppose I have a function f. Alright. So we can tell that this function is continuous as we don't lift up the pencil. But if I say that this point over here is a, and this is f of a, we can clearly see that the function is going to approach f of a from both directions. So the way that we're going to test if these functions are continuous or not is we're going to be taking some limits. Very fun, right? So we are going to take the limit as x approaches 3, as that's our point of interest, of f of x, which is negative x squared minus 3. And we want to see if that's equal to negative x squared, or really just 3 squared minus 3. Well, this is going to give us a negative 9, so negative 12. Let's plug in, use direct substitution over here, and we also get negative 12, so the answer is yes. We want to show that g of x is equal to ln of x is continuous at x is equal to e. So we're once again going to take the limit as x approaches e this time of g of x, which in this case is the natural log of x. And we want to see if that's the same thing as the natural log of e. Well, if you know your exponential and logarithmic rules, you know they're inverses, so they undo each other. So this is just a 1, and as x approaches e, we can use direct substitution, and that also approaches 1, so yes, this function is continuous. Continuing on, well, we can take the limit. I don't want black. Black is a horrible color for this. So we can take the limit as x approaches negative 2 of 1 over x plus 2. And we want to know if that's equal to 1 over negative 2 plus 2. But wait, we have a problem. Whereas we might be able to define this limit somehow and find what's equal to, this point here is undefined. So this point is not, or this is like going to infinity. In fact, it's going to plus or minus infinity. Or really, it does not exist. Whereas this other half is going to go to plus or minus infinity. So is this continuous? No, it is not. Next thing we need to cover is when is a function not continuous? And we have 3 main types of discontinuities. So we have a whole or a removable discontinuity. And the reason why it's called a removable discontinuity is, let's say this function is h of x. We can often define a new function g of x that will fill in this hole. And you might ask, why do we want to do that? Well, it is useful in calculus to be working with continuous functions. Continuing on with our next example, this is another whole/removable continuity, but it's defined at a different point. So in this case, h of x was undefined, but the limit existed. In this case, h is defined, but the limit does exist, but they're not equal. An infinite discontinuity is what happens whenever a function is going to approach an infinity at a certain point. A jump discontinuity is possible to fix, but it's incredibly difficult, so we won't be doing it. So what this is really saying is these 2 points have 2 different limits that they approach. So the limit from the left does not equal the limit from the right. So in this case, the limit does not exist, but the function is defined. Continuing on, we now have continuity at an interval. A function f is continuous on an interval if it is continuous for every number in said interval. Well, how can we show that? And I've got an example planned out for you. You might recall that our definition of a function being continuous is if the limit as x approaches a of the function is equal to the function of a. Well, let's use some algebra here. Let's take the limit as x approaches a of sine of a, or of sine of t, and we want to know if it's equal to sine of a. Well, we can use direct substitution since there's nothing really wrong with that point, so we get sine of a is equal to sine of a. So yes, it is continuous in the interval. Continuous in the interval. Alright, continuing on. So I wanted to now ask, what type of discontinuity is, or discontinuities are in the following function? And there's 2 of them. I'll give you a moment if you want to try it yourself. Identify them. Okay, I've given you a moment. So the first one I'd like to identify is there's very clearly a whole / irremovable discontinuity. Continuity. And the second one is going to be an infinite discontinuity. Discontinuity. All right. So now we want to show if f of x is continuous again. So once again, we're going to use the definition of being continuous, which is if the limit as x approaches a of f of x is equal to f of a. Well, let's see. So we have the limit as x approaches a of x cubed plus 4x plus 3. And is that equal to a cubed plus 4a plus 3? Well, we can always break this down into more limits, but I don't think we have to. I think we can see this is going to be a cubed plus 4a plus 3. Well, both sides are equal to each other, so as thus, the function is continuous, or f is continuous. Continuous in the interval. Which is really, since I didn't specify one, that it's all real numbers. Alright, my next question, and we're already halfway through this. Jeez, I am blowing through this. Alright, continuing on. We have 4 properties of continuous functions. So if f and g are both continuous, then f plus or minus g c times g, c is just a constant, f times g, and f divided by g, as long as g of a is not equal to 0, all of the above were continuous functions that can be composed of those. So, all the following functions and all numbers in their domain are continuous. So, for example, a polynomial is continuous for all real numbers, no matter what. A rational function is continuous as long as g of x is never equal to 0. A root function is continuous, and roots are kind of special, but it will be continuous for all real numbers if odd, and I'm going to mean like this root out here is odd, but it will only be for positive numbers, or 0 greater than 0 to infinity. And of course that domain can change, or where it's continuous can change depending on where, if you have a shift in your domain. Trig functions are always continuous as long as their denominator is never equal to 0. So that's primarily just for the tangent, cotangent, secant, cosecant, but cosine and sine are continuous for their entire interval, for all real numbers actually. Going on, inverse trig functions are continuous for all numbers in their domain. So depending on the trig function, it could be from like -1 to 1, or it could be all real numbers in the case of tangent and cotangent. Exponentials are continuous for all numbers in their domain. However, logarithms are only continuous for 0 greater than infinity, not including 0. Alright, continuing on, I actually have a multiple choice problem, which is kind of unique. So, I wanted to ask which of the following is continuous from 1 to infinity. Give you a moment, you can think about this. So, we know that this natural logarithm of the absolute value of x over x is going to be continuous, as nothing there will be discontinuous from 1 to infinity. So I'm going to put a big old x underneath it. Sine of x over cosine of x plus 1. Well, if cosine is -1... Ooh, give me one moment. I just realized. There we go. Now it's fixed. I forgot a 0.1. If not, both b and another one would have been discontinuous, but b is not supposed to be. So no matter how small this cosine value gets, which at max it will be, or at minimum it will be -1, it's still going to not be equal to 0, so it won't have an infinite asymptote. So this value, b, is also going to be continuous. The logarithm is not going to be continuous, and the reason why is it's shifted 4 to the right. So it's like 1, 2, 3, 4, 5, 6, 7. Alright. And it has this asymptote here. This asymptote makes it not continuous on the interval that we were asking about. Alright. So we know that this one is the right answer, but let's go into why these other ones are also work. So e to the 5x, that is a continuous function. And we have that over another continuous function, and this denominator is never going to be 0, so this is continuous. And then finally, we have an odd root, which we know this is all real numbers for where it's continuous, and this 9x cubed, which is also all real numbers since it's a polynomial. Continuing on, I wanted just to go over a small bit more limit rules. I know there is a ton of these, but this one's a bit easier. The limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. So I've just got 2 practice problems here. They're really not that bad. So what we want to start out by doing is taking the limit as x approaches 1 of g. Well, at 1 of g, that looks to approach 1. And f of 1 looks to be about -1/2. Alright, continuing on, as x approaches 2, well, g approaches 2, and that looks to be approaching -1. Alright, Continuing on, we now have the intermediate value theorem. Okay, so this theorem is a fundamental theorem in calculus. Well, it's not the fundamental theorem of calculus. No, sorry if that confuses you. But it is a very major theorem. It is, if you're in like AP calculus, you need to know this theorem. It's one of the ones that are required. But suppose f is a continuous function on a closed interval from a to b, and f of a is less than or equal to n or less than or equal to b, where a does not equal b. There is a number a in the interval, in the open interval a to b, such that f of c is equal to n. So if f of x is equal to x squared on the interval 0 to 5, find a c such that f is equal to 16. Alright, so in this case, we first have to prove that we can use the intermediate value theorem. So especially in AP calculus, you're going to want to say, because f is a polynomial, and you might ask, why do we want to say that? Well, we have to state all the conditions that it meets. So it's a continuous function. Why is it continuous? It's a polynomial. Because f is a polynomial, it is continuous for all real numbers. Okay, now, what's it called? The next thing that we need to show is that, we need to first show that it's on a closed interval. And, comma, f is on a closed interval, from a to b, or from 0 to 5, since we have to state that exactly. Now, what is f of a? Well, and f of a, well, we're doing with 0 here, so f of 0 is 0. So 0 is less than or equal to n, which is less than or equal to, well, what's b? What is going to be our v value? Well, that's going to be 25. There must be a c value, a value c, such that f of c is equal to 16. Well, we know that since we're just plugging in c, we can say that 16 is equal to c squared. Take the square root of both sides, and we get a plus or a minus 16. Square root of 16. So c must be plus or minus 4. Well, that would be two values in our interval, wouldn't it? No, it's not. So we have to see which one of these values is within our interval. So c is actually going to be equal to 4. And we want to also make sure that we state we can use the intermediate value theorem, the IMV, we can abbreviate, IVT. And we can find that c is equal to 4. Alrighty, friends, that's it for you today. I hope you have a wonderful rest of your evening, and hope you found this video informative. Have a great rest of your day. Bye-bye.